Now that we know how to calculate the pH of a buffer solution, we can actually take that a step further and figure out what pH will be after we add an acid or a base. But we do have to think about this in two separate parts. So the first part is the stoichiometry. So how much of the added base or acid is going to react with our buffer solution. So we have to think about how much is reacting and how much is going to be left at the end of that reaction. And then we have to do an equilibrium calculation using those new values for the HA and the A- after the reaction occurs. Okay, so we can think about this. One way to look at it pictorially is we're starting with HA and A-, so we're starting in the middle of this picture, and depending on what we're adding, if we're adding acid or if we're adding base, how that's going to change. So if we add acid, it's going to react with the conjugate base, and we're going to end up with more HA after the reaction. If we add base, it's going to react with the acid, the HA, and we're going to end up with more A- after the reaction. And then those new values are going to be what we use in our Henderson-Hasselbalch equation. Let's look at an example where we're calculating the pH of a buffer that is 0.1 moles of acetic acid, 0.1 moles of sodium acetate in 1 liter of solution. We're going to look at two different cases. So let's start with no sodium hydroxide added. To calculate when there's no sodium hydroxide added, we're going to use the Henderson-Hasselbalch. Which is the pKa plus the log of the basic form over the acidic form. So let's put our numbers in here. We know the pKa of acetic acid is 4.74 plus the log of, if we have 0.1 moles in 1 liter of solution, that is equal to 0.1 molar divided by, again, 0.1 molar of the sodium, of the acetic acid. So if we take the log of 0.1 divided by 0.1, that's the log of 1. The log of 1 is 0, and so when we have equal amounts of acid and base, our pH is equal to our pKa. Now let's look at the case where we're adding 0.1 moles of sodium hydroxide to this solution. So if we're adding 0.1 moles, we're going to have our sodium, or our acetic acid, plus the OH minus, and that gives us our acetate plus water. Okay, again, water is not going to be used in our reaction or in our calculations, but just to make our equation balance, we're going to include it. Now, this isn't exactly an ice table. This is more looking at stoichiometry. So we're going to look at moles before, moles added, and moles after. So moles before, we know that we have 0.1 moles. Before our reaction, there's 0 moles of the base, and we have 0.1 moles of our conjugate base. Now we're adding 0.01 moles of our base. Okay, so after that base is going to react with our acid, it's going to remove 0.01 moles of the acid, and after our reaction, we're going to have 0.09 moles of the acid. There's going to be essentially none of the base left, but when that reaction happens, it forms an additional 0.01 moles of the conjugate base. So when we add that to what we initially had, we end up with 0.110 moles of our conjugate base. So now, after our reaction, we can look at our Henderson-Hasselbalch equation again. And we have the pKa plus the log of the basic form divided by the acidic form. So it's no longer 1 anymore. And so we've got more of the basic form than the acidic form, so we would expect the pH to increase. So our pH is 4.83. So the change in pH that we saw is going to be 4.83 minus where we started before we added any base. So our pH has increased by 0.09 pH units. Now if we think about how this is, what this compares to, if we just had the base in solution, we'd start with pure water, which has a pH of 7. And if we added 0.1 moles to 1 liter of solution, then our pH would be a pH of about 12. So in that case, so if it was in pure water, okay, we would have our change in pH of 12 minus 7 for our pure water. So we would get a change of 5 pH units versus 0.09 when we're in the buffer. So having that buffer is drastically diminishes the change in pH that we see. Here's a practice for you to try. When we add hydrochloric acid to a buffer solution made up of hydrofluoric acid and potassium fluoride. See if you can calculate the pH after that acid addition. If we're adding acid, it is going to react with the anion part or the conjugate base part of our buffer. And so we're going to look at the moles that we started with, moles before the addition, moles added, and moles after. So before we add the acid, we have 0.071 moles of the conjugate base. We haven't added our additional acid yet, and because of our buffer solution, we have 0.14 moles of our acid. So we are adding 0.02 moles of the acid, and that 0.02 moles is going to react with the conjugate base, decreasing the base, the F minus, by that same amount. So we're going to end up with 0.051 moles of F minus. That acid is going to be completely used up and going to be converted into the acidic form. So we're going to add the 0.02 moles to the acid. So we subtracted it from the base, added it to the acid. So now we can calculate what our pH is going to be, because it's equal to the pKa plus the log of the basic form, which is F minus, over the acidic form, which is HF. And so if we plug our numbers in, our pKa is 3.15 plus the log of 0.051 divided by 0.160. So we have more in the acidic form, and so that is going to lower our pH. We'd expect a pH less than 3.15. And in fact, we get a pH of 2.65 for the addition of 0.02 moles of HCl to our buffer solution.